Also, a problem with table lookup is the fact that this grid can never change. It has to be static in order for the table to actually remain plausible. If it's the case where units can be placed dynamically, say like structures that are going to change the paths that are available, you can't use a table, or you have to be able to dynamically cross off rows or columns as is necessary. Um, you know, if this isn't a problem for your game, then table lookup is really good. If this is a problem for your game where you have structures being built, or end users can mod the game, change the layout of the nodes, then this is something you definitely want to avoid. And thus the alternative, which is path searching algorithms. So instead of having a table pre-computed, you're going to compute these on the fly, try and figure out the best route given your current situation. Um, you know, you don't have to worry about anything being dynamic because it's done on the fly. So there are four common search algorithms: breadth first search, Dijkstra's algorithm, best first search, A-star search. Um, and so going through each of them, the book has a couple examples of each, or rather they have an example of each. Breadth first search is a very simple search, something you might come across commonly in a data structures class, um, or an algorithms class. Um, the benefit of breadth first search is that it makes some assumptions about the cost of moving to nodes. It doesn't really work well for real world pathfinding where um, nodes aren't necessarily directly next to each other. There may be some cost along the path to get from one node to another node. Um, Breadth first search just automatically assumes that the next best path to search is the next node, whereas Dijkstra's algorithm takes this into account and actually assigns a cost to the movement of each node. Um, Dijkstra's algorithm also, because of that, will always try and find the best path first, whereas breadth first search will not. If there's a cost associated with the path, it doesn't take that into account. And Dijkstra's algorithm does this by having a priority queue, basically um, spitting out the next shortest possible path when traversing through the different nodes, in addition to also having code to double check that there aren't any other shortest paths along the way. Um, and so Dijkstra's algorithm is usually used um, in the instance where you don't have a lot of obstacles. And so Dijkstra's algorithm is used where you need to find the best path, um, and you have a node structure whereby you have different uh, costs for moving between the nodes. Breadth first search maybe works well in the case where each node, the traversal from each node is the exact same cost. Another issue with Dijkstra's algorithm is it in general, sweeps the entire grid at the same distance, so it's not very efficient in focusing in on the correct region um, for the destination. Two kind of solutions to that are best first search and A-star search. So best first search will try and find the optimal path first, um, without taking into account any knowledge of the actual grid. So this has its problems in that it will, if there's like a concave area, let's say kind of like a cave, where there would be you're trying to get to the other side of it, it will try all possible paths through that before actually trying to traverse around it. The other option that I mentioned is A-star search. A-star search uses a heuristic, which will basically try and give an associated cost to each particular node. The example that's given is, the straight up, uh, bird's eye, the distance between 2 points. So if you could actually traverse directly between them. It's the square root of the sum of the squares. A squared plus b squared is equal to c squared. You just create a triangle and figure out what the hypotenuse distance is. However, you can also change the heuristic in A-star search to take into account other knowledge, like there's a wall in a certain region, or some other prior knowledge about the terrain, so that rather than trying, like as I was saying, a best first search where you're going straight for a particular spot, to avoid it. And so A-star search also finds the optimal path, and in general is used for the most part. There are some situations where you would not want to use A-star search, and you may want to use the best first search. In particular, this is where you're crunched for performance. Best first search is much easier to compute, but like I said, it has those problems. So if performance is an issue and you do decide to go with best first search, you want to design your levels not to have any concavities. If performance isn't an issue, you have plenty of computing resources at your fingertips, then you're probably going to want to go with A-star search. So the last topic that this chapter is broken out into is the idea of path following. So you've got your node, you got your grid, where your different units can move, you figured out a path, you know exactly how to get there. Now, what sort of problems are you going to run into with this? Are you going to actually be able to get to that node? Is there going to be some other unit in the way before you can get there? When we do our computations, we're not taking into account any other nodes. You can add parameters for whether or not a node is already being used, but do you always want to do that? Do you want to just leave it open? Do you want to assume that other units can move around? So one way around this is to leave space between units on the map. Things like if you have a group of soldiers, so long as there's a little bit of room around it, it makes sense that they can go kind of next to each other. So this works for small units with a relatively large amount of space around them. This isn't always the case for larger units, say like tanks. Tanks need a lot of room to move. They can't really slip by one another just like two human beings can walk past one another. And it looks very awkward if you try and do that. And so you can try and, in that case, you could try and find an alternate path around the block in the best route. Basically generate another path, assume that that path is blocked, mark off the node that's blocked, and try and see if there's another path. If there is no other path, you could just fail and basically have the unit not move at all, so what they're calling assume no paths exist. And yet another solution would be to try and ask the blocking unit to try and move out of your way, and then find a spot for it to move, and then try and traverse your first path that you found. Obviously, if the blocking agent moves, the blocking unit moves, you want to make sure it doesn't move into a spot that'll block you just one step further down the line. So in summary, the different pieces that make up pathfinding are pathfinding systems, the actual network, path planning, so that's figuring out how exactly you want the units to move within before they actually get there, searching for the correct path, so finding the exact route that you want to go, and then path following, which is adapting for any obstacles that you're going to run into along the way. So just to go back on some of those initial questions that we had at the beginning of the chapter. What are the advantages of manually generated path networks versus an automatically generated network? So an automatically generated network, you kind of get this regular structure, and it doesn't always work best depending on your game. Some games works well, others it does not. Versus manually choosing a path, you'll actually get very well defined behavior